My name is Jun Nishida. So today I'd like to introduce our exoskeleton called DigituSync. And this work has done with Yudai Tanaka, Romain Nith, and Pedro Lopes at the University of Chicago. So as here you can see, this exoskeleton can synchronize two users' fast and precise finger gestures. Then what can we do with this? Okay, so as here you can see, users can even learn how to play a piano by connecting fingers. So this is just a glimpse of what we wanted to explore, which is how can we share dexterous hand gestures between two users instantly and easily. So why do we need to do this? So let's imagine a student learning a piano from a teacher by observing it, sitting aside each other. So the piano teacher is now trying to explain which finger, a correct finger force to push a key, and correct timing to play a note, with correct finger combination, which is chords in this case. And these are all important motor information, but also hard to memorize all of these quickly. And knowing this information is also important for piano teachers to understand students' skill development. Then the question is, how can we directly communicate this motor information to each other instantly and easily to support faster learning in a traditional piano learning setup? And of course, there are many ways to communicate this. One of the major way would be using the active globes, using the sensors and actuators, such as using electric motors, pneumatic actuators, wire actuations, or even electrical muscle stimulation for controlling individual fingers. And all these active globes are great, but these also share three critical limitations, especially we want to try to incorporate this into the educational setup. So first challenge would be end-to-end latency, which is always problematic in skill sharing because of the combination of sensing, actuating, and also computation. Even with 20 milliseconds of haptic delays, we can notice that, and it affects learning performance. And because of this, they need high-precision actuators and sensors, and they are very expensive. And some exoskeleton available on the market can cost up to $20,000, which is a major challenge when trying to use this in a classroom setup. Lastly, they are not always 100% safe, as it could provide a large and external forces from the batteries or motors. But looking back, some of works in robotics and the HJ community, passive mechanisms have been also actively employed because they can provide real-time and high-fidelity haptic feedback with human-safe walk-up use and low-cost form factor. Examples include using physical linkages or hydro tubes for controlling remote robots, or even microstructures for sensing, actuation, and even computation. And that's why we found the potential of using the passive mechanisms for communicating complex haptic cues across users. So in our approach, we employed mechanical linkages for sharing every haptic cue for finger gestures across users that can be easily installed and operated by the end users. So now let's see how we design an exoskeleton. So our exoskeleton consists of 4 components mainly. Finger sockets to connect fingers and the exoskeleton, and finger motion transmission mechanism between two users, and a palm base that holds the mechanism itself, and a wrist linkage that connects two users' wrist movements. And of course, the most important part is the finger motion transmission mechanism, and here shows how it works. And as here you can see, each finger's movement is transmitted as well as force smoothly while bending a finger. And by having this for each digit, it can share multiple finger gestures between two users in real time, which would support interpersonal skill transfer in an educational setup like this. And in addition to this, each linkage has a magnet inside so that teachers can attach and detach from the students. And because it's mostly 3D printed, it costs only $40. So does this really support hand skill transfer from one to another? So to prove this, we went back to one of the examples, which is the 2 users in piano learning. So in this study, we investigated how the exoskeleton impacts the user's learning performance. And the participants were given 10 trials for learning and replaying these 2 melodies. And as for the interface conditions, we compared to a traditional feedback manner where a teacher demonstrates the melody in front of the students, which is widely used in the current setup. And in the DigituSync condition, participants learn the melodies by connecting fingers by the exoskeleton. So here shows the error in notes and intensity during the replay. And we found that participants learned and replayed the melodies with significantly less errors in both notes and intensity. And from these results, we think this exoskeleton can be introduced in the traditional piano class and enhance haptic communication between teachers and the students. But we also know that active ropes have their own great benefits too. In particular, it can provide adaptive feedback based on the learner's need. So what is adaptive feedback? So let's think about student skill over time. As students learn more, their skill would improve like this. In this case, teachers' feedback should be reduced in response to the students' learning curve, like such. And this is very important in motor learning because it affects learning motivation as well as learning agency. And then question is, how can we incorporate the function of this adaptive feedback into the exoskeleton configured in the passive form factor? And here is our answer. So we designed variable length linkages that allow to change the shape of the exoskeleton. So by changing the shape of the exoskeleton itself, teachers can adjust the amount of force feedback to the students. So as here you can see, by just changing the shape of the exoskeleton, the force transmission ratio can be adjusted like this. So now we investigated how this variable linkage could improve the user's learning experience. So in this study, we explored how the variable linkage can improve the feeling of control over own finger movements. And to provide adaptive feedback, the amount of force feedback was adjusted based on the performance after every trial. And we compared the performance as well as qualitative feedback between static length condition and variable length condition. And here shows the results. And although we did not find any difference in the performance, we did find a difference in the user's subjective feeling. And this shows the feeling of finger control over their own finger movements while receiving the haptic assistance from the teacher. And with the variable length linkage, participants felt their fingers are more in control by themselves, thanks to the adaptive mechanism. And the participants also mentioned that with the variable length linkage, the haptic feedback from the teacher was more responsive compared to the static length condition. So overall, our variable length linkage have provided the function of adaptive feedback with the exoskeleton configured in the passive manner. And we believe there's a range of interesting motor learning scenarios where we can leverage the benefit of DigituSync, such as teaching more complex gestures like finger blade training for deafblind persons, as they need to memorize tons of gestures with different finger pressure. Or directly navigating a blind person's fingers and arms to teach how to use new tools, like such. And actually, we carry out exploratory sessions of some of the scenarios. And we found that professional teachers and deafblind users could use our device instantly without having any prior exploitation, training, or instructor at the venue. And they also used our exoskeleton not just for teaching, but also monitoring by themselves. And we think this proves one of the benefits using the tangible and passive form factor of the exoskeleton. Okay, so today we talked about how can we share dexterous finger gestures between two persons instantly and easily through this exoskeleton, and how it can improve the learning performance as well as subjective feeding during the training with the adaptive mechanism. Okay, thank you very much, and happy to have questions from you. Thank you.
Have you considered other positions in our body, like feet or ankle or
Okay, that's a very interesting question. So this time we focused on the hands because the hands are very important interface between human and the surrounding world, and that's how we learn new concepts. But yeah, synchronizing legs sounds very interesting, but we also need to think about how to maintain the balancing when it's shared with other people. So that would be a interesting topic too.
maybe by designing a whole wearable system, we can replicate others' physical behavior.
Yeah, that would be also interesting. But in that case, we also need to consider how we can preserve the sense of agency of the user, because we also need to feel the sense of agency to maintain our motivation. So yeah, maybe using the adaptive feedback in the same way could help that. Thank you.
Another question is that have you considered about using EEG or EMG some psychology measures to detect the user's feeling, and therefore the teacher can feel what the students is thinking about in the same time and can obtain feedback from the user
Yeah.
students?
So actually, this is a very first prototype of that kind of semi-passive version. So we also linked exoskeleton with the EMG signals so that exoskeleton can detect the amount of activity and automatically change the shape of the exoskeleton for more smooth adaptive feedback. Yeah, thank you.
University. This is really interesting.
Thank you.
I've noticed in many of the videos is there's a huge difference between the finger angles on the upper teacher's hand and the lower student's hand. And that's most people don't play piano like this. So you're indicating which finger to use, but there's nothing about the way the finger should be closed. It's really good communicated.
Yeah, that's a.
Thought about ways of trying to fix that.
Yeah, so that's a great question too, and of course, because of the physical, the design of the physical linkages currently we have, we cannot have a complete grasping motion. But we can also use a different type of passive components like hydraulic tubes that can transmit some angular displacement of the finger joints that could reproduce complete grasping gestures. So maybe we can use alternative mechanism to achieve the sharing of the grasping gestures. Yeah.
Exoskeletal systems have stuff on the backs of the fingers, as opposed to they all on the inside, which makes it very hard to really bend it.
Yeah, so we also tried a very simple type of the exoskeleton that just connect fingers by using very simple groove. But actually, because the joint center is located inside the finger, so as you bend, there's a very big gap. So and it didn't transmit the gestures very well. That's why we needed a very big linkage in between.
Thank you.
And
Okay, thank you very much. I have a very small announcement that I'm going to open my lab at the University of Maryland from next January. And now I'm hiring students, so please feel free to reach out to me during the conference. Allow me to have a quick lightning talk. I have been exploring how we can share physical experiences across users by using wearable devices, such as sharing muscles or fingers, or changing bodies into another person, such as into a child for supporting product designers, or even investigating the sense of agency in haptic devices and wearable devices, like this. And University of Maryland Computer Science just got a brand new building with a big maker space inside like this. And of course, there is a Professor Haishu Pen, who does a lot of research in fabrication, maybe here or in the next room. Oh, there, great. So feel free to ask him about his lab as well. So we are looking forward to your application. That's all.